So let's do a quick calculation. Let's go ahead and move the observation point, intentionally choosing this first quadrant that you might be familiar with. So what I'm going to do is let's go ahead and draw a reference axis, because we have to have a reference coordinate system. So here I'll call this the y-axis, and if I draw that little arrow, I can go ahead and give this y hat. You might be familiar with IJK as the coordinate references. I'm going to go ahead and give it y hat. And then now I'm going to draw the x emanating from here. Okay, so just in 2 planes. We'll do 3 dimensions probably later. And of course, this is the x hat direction. So now, obviously, this is a coordinate system that is centered directly on top of the source charge. We don't have to do it that way, but it works out incredibly convenient for what we're trying to do. Now, if I draw R, so this is coordinate x equals 0, y equals 0. So I'm drawing the line to my observation point. And I'll try to make it clear that I'm looking at the middle of that observation point. That's pretty important. Okay. So I don't want to confuse anything with a discrete, or I should say a finite size circle. This should actually be a very specific, unambiguous point, but it makes more sense to draw that as a circle here. This is my variable r. That's the displacement. The vector r is something that we'll determine in a second. So what I can do now is, if I look at my equation over here, so forget the definition, we're looking at the equation. I can start to assign variables here, and we'll go ahead and make an estimate of what this field is going to be. So a couple things we have to know. What are the quantities? Well, the units that we are using right now are SI units. It's metric, and we'll probably talk about that a little bit more in a subsequent session. Q is the value of charge, so I'm going to go ahead and make Q equal to 1 coulomb. For these numbers here, we know 4 is just a number. We know what the value of pi is. This epsilon naught is something that you may or may not be familiar with. This is the permittivity of free space. And the value of this is 8.854. And this is scientific notation. Hopefully you're familiar with that. Times 10 to the negative 12. And there are different representations that we can use still within SI units, but the units that we're going to use for this are going to be coulombs per volt meter. And that can be a mouthful, and we'll probably talk about that at some point as well. So now we're going to define R. In this case, we're going to set R, let's say, equal to, we'll make it small for the sake of the next segment. We're going to say 0.1 meter. So I'm not going to worry about the direction at the moment. So what I want to clarify here is, over here on the right, I'll go ahead and write out the magnitude symbol. So if I say magnitude of the electric field as a function of R, what that basically means is that I want to ignore the vector nature of it, and I'm only concerned about the impact of R as the displacement. So if I write this out, just to be perfectly clear here, if I write this out, I'm going to go ahead and say Q, just like before, 4 pi epsilon naught on the denominator, and now I'm just going to say 1 over r squared. Now here's the key. I said magnitude of this, which means now you no longer see a reference to the r hat vector. And we'll calculate this as a magnitude first, and we can come back and add the vector quantity to it as well. So let's rewrite this with the actual numbers now. So if I say the magnitude of E of 0.1 meters, to be very explicit here, then let's go ahead and fill in the rest of our units here. So Q we wrote down as 1 coulomb divided by 4 pi, and I'll say 8.854 times 10 to the negative 12 C per voltmeter. So this can get very complicated. So I'll just do my best to keep track. Notice we have the large fraction, and then with the units we have that small fraction in there as well. 1 over r squared, I'm going to go ahead and multiply these two fractions together. So I'll say 1 divided by, in this case, it's going to be 0.1 meter squared. So after copying and pasting our calculation into the whiteboard here, 8.99 times 10 to the 11. So that's a huge number. Just as the epsilon naught was a very small number, it makes sense that this is so large with that being in the denominator, and you can certainly work that out. Notice, of course, this is just the number. We don't have the units. We did not punch those units into the calculator. So I'm going to carefully write them out just as a quick check to make sure that we get the right thing. So notice we've got a kind of a complicated fraction here. I'm going to rewrite the units alone, and I'll just go ahead and write them over here. So coulomb divided by 1 over, I'll go ahead and say coulomb meter squared, and that's divided by volt meter. So if you remember how to handle that, we'll go ahead and flip this. I'll write it down here as coulomb over 1 times, and we're going to invert the denominator. So I'll say volts meters on the top with coulomb meters squared on the bottom. And if you remember how to cancel, I've got coulomb in the numerator and then in the denominator. I'm just going to draw a line through those, and they don't cancel to 0, they cancel to just 1. And then now I've got volt meter over meter squared. I can get rid of this meters in the top, and I can remove the exponent. So if you can carefully see what you have left there, it ends up being volts per meter. And I'll just go ahead and write that in here, and volts per meter. And this is the answer for our magnitude of the electric field due to a point charge of 1 coulomb at a displacement of 0.1 meter or 100 millimeters away.